In 14.5, we're going to build upon our knowledge of double integrals and introduce triple integrals. So let's dig right in here. Definition: the triple integral of a continuous function f of x, y, z of three variables over the region G is defined exactly as written. So I have a remark here that's going to talk about several of the properties of triple integrals. The first one says that constants can be pulled out front. The second property says that the triple integral can be distributed across sums and differences. Of course, we know that's not going to be true with products and quotients. And finally, property 3 says that you can split up your region G into two regions, G1 and G2. And after subdividing, then you can carry out the sum of those two triple integrals. So let's take a look at a first example here that's already set up for us. We want to evaluate the iterated integral. So what I'm going to do to begin here is to just kind of draw in these lines here so that we focus our attention on the innermost integral, which is, of course, with respect to y. All right, so x is going to be a constant here, and the integral of e to the y is itself. So I'm going to recopy my first two integrals. And my integral of x e to the y is x e to the y. I want to evaluate y from 0 to the natural log of z. And then I'll carry out my z integral and finally my x integral. So rewriting my first two integrals, I have e to the natural log of z minus e to the 0 dz dx. Now, of course, we know that the natural exponential function and the natural log function are inverse operations. So that's just going to give us z back out, and e to the 0th power is 1. So let's write our simplified integral from 1 to 3, from x to x squared of xz minus x dz dx. All right, so now let's go ahead and integrate with respect to z. That's going to give me a 1/2 xz squared minus xz, where z is running from x to x squared dx. So now let's go ahead and plug those values in for z. So that's going to give me a 1/2. Let's see, x squared squared is to the 4th times another one is to the 5th minus x cubed. Take away 1/2 x cubed minus x squared. All right, now before I dive right into my final iteration of an integral, let's go ahead and distribute this negative. And furthermore, we'll combine. We have a negative x cubed minus a 1/2 x cubed is going to be a negative 3/2 x cubed. All right. So we have our integral simplified, and now we're back to just a single variable integral from Calc 1. This is going to become a 1/12 x to the 6th minus a 3/8 x to the 4th plus 1/3 x cubed, where x is ranging from 1 to 3. So this is 1/12 3 to the 6th minus 1/8. I'm going to write this as 3 to the 5th, so I'm including that 3 there. And a 1, actually this one will just be 9. 1/3 3 cubed is just 9. Minus evaluating at 1, which is a 1/12 minus 3/8 plus 1/3. And I tell you what, I'm not even going to spend any time simplifying this. It's ugly enough. Just going to leave it right like that. So, and I completely encourage you guys to do the same on quizzes and exams. I'm not as concerned that you can do arithmetic and more concerned that you can do calculus in this class. All right, so triple integrals, just one more iteration, but the process is exactly the same as we've seen in single integrals and double integrals. We have an analog to Fubini's theorem in 3 dimensions. We're going to let G be a rectangular box defined by the given inequalities. So notice that all of those variables A, B, C, D, K, and L are constants. If f of x, y, z is continuous on this region, then we can replace the triple integral dv as a dz, dy, dx with the appropriate limits of integration. And there's a little clause there at the bottom that says, moreover, the iterated integral on the right can be replaced with any of the 5 other iterated integrals that result by altering the orders of integration. So in 2 dimensions, Fubini's theorem said that dA can be written as dx dy or dy dx. The order of integration didn't matter. In 3 dimensions, Fubini's theorem is saying that dv can now be written as dz dy dx, dz dx dy, dy dx dz, et cetera, et cetera. There are 6 different ways that you can organize those differentials, and the order of integration doesn't matter. All right, our next theorem, theorem 2, says let G be a solid region with an upper surface defined by G2 and the lower surface defined by G1, and then let R be the projection of G onto the xy plane. So as long as your function f is continuous on G, then the triple integral over G of f dv can be written as the double integral over R, again, where R is the projection onto the xy plane, of your integral in the middle that says you have your upper surface on top and you have your lower surface on bottom. This is with respect to z. And then finally, you have your dA out back. Now, again, your dA is going to depend on your region. Is it going to be vertical slices, in which case you have dy dx? Is it horizontal slices, in which case it's dx dy? Are you working with a polar region? Is it r dr d theta? So you'll have to identify that using your knowledge from 14.1 through 14.3. But this theorem is telling you that the innermost integrals should be in terms of z, where your upper limit is your upper surface and your lower limit is your lower surface. All right, so to recap, how are you going to find your limits of integration? So find your upper and lower surfaces, and those are going to serve as your z limits. Then we want to project z down to 0 so that you're looking at the xy plane, and you want to sketch this projection. This sketch is so crucial. That's how you're going to identify your order of integration in terms of x and y, or whether it's a polar region, such that you would use polar coordinates to compute your integral, and then determine your limits of integration appropriately. We have one more remark here that says you can also use triple integrals to evaluate a volume of a solid region G. And notice that you're just taking the triple integral over your solid region G, and all you're doing is you're integrating 1 dV. So if you want to write a 1 in there, you certainly can, although it's not required. And so your integrand is very simple. It's just a matter of figuring out what your limits of integration are going to be. All right, so let's use this remark to compute a volume. Use a triple integral to find the volume of the solid. So 16, we want to find the solid bounded by the surface, z equals the square root of y, and the planes, x plus y equals 1, x equals 0, and y equals 0, or excuse me, z equals 0. So remember, z equals 0 is just the xy plane, and x equals 0 is the yz plane. And then what I'll do for this other plane, I'm going to write it as y equals negative x plus 1 so that I know how to sketch it. And let's go ahead and attempt to sketch this region, or this solid, I should say. So here's my x, y, z coordinate axis. First, I'm going to plot the equation of z equals the square root of y. and that's in the YZ plane. And then I just want to extrude that, something like this. Right, so it looks like kind of this bent sheet of paper that's attached to the x-axis. Right, now in a different color here, I'm going to plot this plane y equals negative x plus 1. So on the y-axis, it has an intercept at 1. On the x-axis, it has an intercept at 1. And so it's coming across here, and then we want to extrude along the missing variable, which is z. Now I extruded up, but you could also extrude down, of course. All right. And then of course, we're also cut off at the XY plane, which is coming out of the plane of the paper, and then the YZ plane, which is in the plane of the paper. So I hope you can kind of imagine the solid that's being bounded by these 4 planes or surfaces. And what we'd like to do now is compute the volume. So remember, the volume is just the triple integral over your solid dV. And so we're going to use our theorem that says, well, we can just compute the double integral of the inner integral, which we have 1 on the inside, where that inner integral is the limits of integration have your upper surface and your lower surface. Your lower surface is z equals 0, right, the xy plane. Your upper surface is that cylindrical surface, the square root of y. So here's our first step. And now what we would like to do is figure out what that region R is in the XY plane. So if I just, again, take my shoe and I stomp down on this surface, what am I going to get when I flatten this? All right. So it's going to flatten straight down because it's like a piece of paper, but remember it's been cut off at this red plane. And so my projection onto the plane z equals 0 looks like the following. So we no longer have the z dimension, we have x and y. And remember, we were cut off at y equals 1 minus x. We were also cut off at x equals 0, which is over here, and y equals 0. So here's our region R. So we're going to use this region to set up our other limits of integration. And so you decide whether you want to do horizontal or vertical slices. You could do either, but I think vertical is probably going to be a little bit easier. So my thickness is in the x direction. This tells me that I want to integrate with respect to y and then x. So I'm going to fill in here 0 to the square root of y, dz, dy, dx. X is running from 0 to 1 on the x-axis, 0 being the smallest, 1 being the largest. And then vertically, I'm running from y equals 0 up to y equals 1 minus x. All right, so I have my volume integral set up. Now I just need to carry out the integration. There are no z's, so when I integrate, I just pop out a z. So I have z where z is running from 0 to the square root of y, dy dx. So in other words, I'm just integrating the square root of y. I'll write that as y to the 1/2 power. So that's going to become a 2/3 y to the 3/2 power. Where y is ranging from 0 to 1 minus x. So this becomes 2/3 1 minus x to the 3/2 power dx. Okay, I could do a u substitution here for 1 minus x. That means du is negative dx. And again, I'm going to change my limits of integration. 0 becomes 1 and 1 becomes 0. Negative 2/3 u to the 3/2 power du, where this negative sign here in front is coming from that negative dx. All right, and so this becomes a negative 2/3 times 2/5 u to the 5/2 power. U is ranging from 1 to 0. That's a negative 2/3 0 minus 2/5. So in the end here, I get a volume of 14 or 4 over 15 cubic units. All right, and that's it for our introduction of triple integrals. Stay tuned for the next section, which is perhaps my favorite section of the entire semester, where we do triple integrals in cylindrical and spherical coordinates.